Let's prove using Lagrange mean value theorem that tan inverse of x is greater than x by 1 plus x square and less than x for every positive real number x. Let's state what Lagrange mean value theorem says. Lagrange mean value theorem states if a function f is continuous on the closed interval a comma b and differentiable on the open interval a comma b, then there exists a constant c such that f dash c equal to fb minus fa divided by b minus a. So we should be able to produce a continuous function and differentiable function on the continuous on the closed interval and differentiable on the open interval. We got tan inverse of x, so let fx equal to tan inverse of x, and we define it on the closed interval 0 comma infinity. Oh, sorry, we can't take infinity. Let's say 0 comma x for n. No, we can't say x, a. So we define fx equal to tan inverse of x on the interval 0 comma a for any a greater than 0. Is this function continuous? Yes. In fact, this function is not just continuous but differentiable, and we know that derivative of tan inverse of x is 1 by 1 plus x square. Then f is continuous on the closed interval 0 comma a, differentiable. It is differentiable throughout R, but we just need f to be differentiable on the open interval 0 comma a. We know that it is differentiable, and we know that derivative of tan inverse of x is 1 by 1 plus x square. So the function is continuous on the closed interval, differentiable on the open interval by Lagrange mean value theorem, or in short Lagrange's LMVT, comma, there exists a constant c, there exists a constant c such that f dash of c equal to fb minus fa, f of a, so tan inverse of a minus f of 0, tan inverse of 0 divided by a minus 0. F dash c equal to tan inverse of a minus tan inverse of 0 divided by a minus 0. We got fx equal to tan inverse of x. However, fx equal to tan inverse of x, and so f dash x, that is d dx of fx, equal to 1 by 1 plus x square. Okay, so f dash c equal to 1 by 1 plus c square equal to tan inverse of a by Lagrange mean value theorem, and that c must be lying between 0 and a, that c must lie on the interval 0 comma a, that c must be greater than 0 and less than a. Okay, if c is greater than 0 and less than a, since c is greater than 0 and less than a, comma, c square is also greater than 0 but less than a square. We simply square it both sides. Once again, c square is greater than 0 and less than a square. Let's add 1 throughout because we want 1 plus c square. We want 1 plus c square. So we just add plus 1. We add 1. We add 1. So we get 1 plus c square lying between 1 and 1 plus a square. Next, we reciprocal it. We know that if 3 is less than 4, then 1 by 4 is less than 1 by 3. So if we reciprocal it, then we find that the inequality reverses. So 1, instead of less than c square plus 1, I'll get 1 is bigger than 1 by 1 plus c square, and that is bigger than 1 by 1 plus a square. But we got 1 by 1 plus c square is exactly equal to tan inverse of a by a. So by equation 1 is bigger than 1 by 1 plus c square, that is tan inverse of a by a, and that is bigger than 1 by 1 plus a square. Now we simply multiply by a throughout to say, or replace a by x to say that x is greater than tan inverse of x, and that is bigger than x by 1 plus x square, and that is true for every positive real number x.